Hey, this is Angie with Beyond the Lecture. Good morning. Thanks for joining me here. Today's review is going to be on acids and bases, basically how to name them, given the formula, and then going backwards, giving the formula based on the name. And of course, just covering some general characteristics on acids and bases. There is an entire unit dedicated to acids and bases, both Gen Chem 1 and Gen Chem 2, and of course in high school chemistry. But before I start, please hit like and subscribe if you'd like to be notified when additional content is put out on YouTube. And again, thanks for watching. And reminder, this review sheet is out on my website. So if you want to get this review sheet, it's about 2 or 3 pages long, and it just covers what I'm talking about here. And you can follow along and make your own notes or just use it as a reference later. Feel free. Go for it. So from the top, we'll start with acids first. And we do have 2 types of acids. We have binary acids. Binary meaning we have 2 elements, only 2 elements here. And you recognize them. Of course, they'll have the acid name on the end here. So I'll go ahead and circle those. There you go. Yeah, you'll see acid. So of course you'll know it's an acid. And we'll have hydro in front of the name. So we'll have hydro in front of the name. We'll have the root of the second element. So for chlorine, we turn it to chlor. And then you simply tack on the ic, and then I'll separate that there to show you hydrochloric and then acid to finish it off here. And do note, I'll discuss this here shortly, aqueous is part of the acid formula. So we have 3 different states of matter, typically in chemistry: solid, liquid, gas, and then aqueous is like a 4th designation. And it simply means that you have something in an aqueous or water solution. Okay, so we know how to identify binary acids now. Again, it's just a hydrogen attached to a single element. Very common ones are hydrogen attached to anything in group 5, 6, and 7. So these are largely, we don't have metals here typically in these particular types of acids. We have oxyacids, that's our second type of acid, and those are hydrogen attached to a polyatomic ion. Okay, so there's another reason you need to know your polyatomic ions. So hydrogen will be attached to, for instance, sulfate or sulfite. Those are the examples down here. I'll just check those with a little blue check mark there. Sulfate and sulfite. So above, if we just look real quick at the rules above here, we have ate turns into ick, ite turns into us, O-U-S, okay? And notice there's no hydro. Hydro is gone. So a way you can determine whether, besides seeing that a binary acid has 2 elements, hydro would tell you that you're working in the binary acid world, and you'd be able to put down that formula accordingly. So that's a review of your 2 types of acids and how you name them or come up with the formula. I'll get into real quick. You'll notice, for instance, down here, I'm just underlining the hydrogens. We do have 2 hydrogens, and I'll show you how to designate those here in a moment. We have a strong acids list. So strong acids are, we can have strong acids, we can have weak acids. Strong acids completely dissociate in water, meaning, for instance, the top one here, HCl, will completely, in the aqueous or water solution, this particular compound will completely separate into its respective ions, okay? And this will become more important as you study acids in more detail. The same for hydrobromic acid, hydroiodic, and so on down the list, okay? So do know there's complete dissociation. They're considered strong. It's only a handful of acids, and anything else not on this list is considered weak, okay? So, which are 10 more. So I would just know these 6 and then know anything else we would consider to be weak. Also, a general rule on your strong acids on the polyatomic side. So I'm talking about these three bottom ones. If the oxygens outnumber the hydrogens by more than two, I think it's two or more, then we can consider that a strong acid. Okay. So for instance, HNO3, we have one H in that molecule and we have three O. So oxygen outnumbers the hydrogen by two or more in that situation. Okay, so we do have some components or characteristics of acids here. They're sour. Lemon juice and vinegar are your two common household type substances that we may see. Vinegar is actually acetic acid. HC2. Gosh, I forgot acetic acid. C2H3O2. I believe that's acetate. Anyway, yeah, we can have hydrogen and attached to the acetate ion. Is acetate. Oop. Check on that. And again, we do produce the hydrogen ions in water. And they do react with metals to produce hydrogen gas. So you might see those types of reactions in chemistry, in your chemistry problems. And matching your protons. So when it comes to determining the formula, you just need to make sure, once you identify it as a binary or the oxyacid, that you choose your anion, and you, based on the charge of that anion, then you just tack on the number of hydrogen protons or ions that are necessary. So for instance, we have H plus and S2 minus. And so basically we need, because this is only +1, right? Hydrogen is only +1. We just need two hydrogens to balance that out. And you can, of course, use the crisscross method that we use with the ionic compounds. So this would be H2S. We'd have two here, and of course, one. So that's an example. And then nitrate, I'll go ahead and remove this real quick because it kind of spilled over. Okay. And nitrate, when it combines with hydrogen, because nitrate only has a +1 charge, I'm sorry, -1. Yeah, then we just have HNO3. Okay, so just make sure your hydrogens, the number of hydrogens balances out the anion in your particular formula that you're working with. Now bases are traditionally they have the OH on the as the anion or on the back end, so you have metals attached to OH, and of course they have the aqueous designation. Now I did forget to put or list the strong acids. These are actually all strong acids, or I'm sorry, strong bases. I listed the strong acids. I forgot to list the strong bases. So these are basically hydroxide ions attached to metals in group 1 and 2. So group 1 and group 2 metals are, when they're put in with hydroxide, they're very strong. So they basically dissociate into their respective ions. So like for instance, NaOH, that's like the most common strong base. They'll completely dissociate to these respective ions in water, okay? And the presence of the OH makes the solution basic. All right, so when we think of bases, think of bitter. So B for base, bitter, that's a way to remember that. It is slippery to the touch, and we have a pH value of greater than 7. And I may have forgotten to mention acids are less than 7. So 7 is like the neutral point in the pH scale. So greater than 7 is basic, less than 7 is acidic. And we're going to turn that litmus paper blue instead of, it's like a purple blue, instead of red on the acids. And to track, so when you're actually putting together when you're actually putting together the base formula, you need to make sure that you have enough hydroxides this time to balance out your metal, depending on what group your metal's in. Okay, so I threw out calcium as an example. Calcium is 2+, and if OH is only, you know, the -1, right? We need to crisscross. Again, you can crisscross or just, you know, mathematically understand you need 2 hydroxides for every single calcium cation. Okay, and notice I put parentheses here and there as well. You need to block those or group those OHs when you add a subscript. Now, sodium attached to hydroxide. Sodium has a +1 charge, OH has a minus. You don't need to, you know, flip anything here. I'll add those there for reference. So yes, calcium with hydroxide, we end up with CaOH2. And, you know, just to recap, I just threw that out there here. Acids have a pH of less than 7. They have a sour taste. And then bases are greater than 7. They taste bitter. Okay, so grand scheme of things, acids have traditionally, they have the H in front, and they could be binary, or they could be what we call an oxyacid. And that's where the H is attached to some type of polyatomic ion. And then the bases have a metal, and then they have the OH attached to it on the anion side. Okay, but when you see aqueous, that's another telltale sign that you're dealing with an acid or a base. All right, so thanks again for watching. I'll go ahead and put a link over to my ionic compound naming. If you want to check that out, I recommend that. To get you started on some naming conventions and et cetera in chemistry. Thanks again for watching. Have a great day.